Right. So let's continue with our introduction to stuff in the complex domain. So we talked about these well-behaved functions before the break. Now let's travel back in time to the, I don't know, 16th, 17th century, where you had these guys like Leibniz and Newton fighting with each other about who invented calculus and stuff like that. And then the idea about entertainment was that people were playing around with series expansions in their free time and looked at what was happening with these series expansion. So let's do something similar. Let's look at convergence of series expansions. And for example, let's look at the function f of x is 1 over 1 minus x squared. Now people had discovered in these days that you could have a series expansion that looked something like this: 1 plus x squared plus x to the fourth, and so on and so forth. And if you kept on adding terms to the series expansion, that you would converge to 1 over 1 minus x squared. At least in some parts of the real axis. So if we have here x and y, if we first draw the function f of x roughly looks something like, my drawing skills leave much to be desired, but let's assume that this is f of x, and it roughly looks something like this. So this is our function f of x. Now in order to get some sort of feel for how these functions evolve, or how this series expansion evolves, let's draw some partial sums. So for example, let's draw first the first partial sum, which is just y equal to 1. So that looks like this. You will agree that this is a very crude approximation to this function, but things get better if we look at 1 plus x squared. If we plot the function y equal to 1 plus x squared, that starts to resemble the function a bit more. And then we can keep on adding terms. So for example, y equal to 1 plus x squared plus x to the fourth looks something like this. And the more and more terms you add to this function, the better and the better you will approximate this shape here. So this also means that this series expansion only converges in the interval from -1 to 1. But people were okay with that because, okay, if you look at this function, it has a discontinuity there. Over here, the function is negative, and by just adding positive numbers, as you can see in the series expansion, they found it logical that you could never approximate a negative function by adding positive values, right? So people understood why this function, why this series expansion only converged in the interval from -1 to +1, because you had a discontinuity at these points, -1 and +1. So that was okay. But then somebody got bored, and let's go back to black. They looked at the function 1 over 1 plus x squared, and then just by playing around with the signs, they discovered a series expansion that looked like this for this series. If you now plot this function 1 over 1 plus x squared, now this function looks something like this. Just pretend that this is a smooth function. Okay, so this is our function f of x. And then people were a lot more hopeful because this function has no discontinuities. So they thought, well, okay, perhaps this series expansion converges in a much larger domain than just -1 to +1, simply because there's no discontinuities here. So they started drawing these partial sums again. So if we first draw the first partial sum, this is again y equal to 1. It looks like this. Second one looks a bit like this. This is y equal to 1 minus x squared. So minus x squared, the parabola goes down. So it already starts to approximate this area of the function quite well. If we then add another term, we get a function that looks something like this. So this is y equal to 1 minus x squared. Sorry, this is a minus 1 minus 1 minus x squared plus x to the fourth. So this is an even better approximation to the function, but still it's a better approximation only in the interval from -1 to +1. Because what you see happening is that alternatively you end up with a final term which either has a plus or a minus. And of course the biggest exponent, the final term, always wins if you go towards infinity. So alternatively you have all partial sums which either go towards plus infinity or minus infinity. So you only get good convergence, a good approximation to that function in the interval -1 to +1. Outside of this interval there's no convergence at all. Either you go to plus infinity or to minus infinity. So this is what's happening here. But this was puzzling people a lot because, okay, this function has no discontinuities that you could observe. So what would then be the philosophical or the fundamental reason why this function does not converge? So if you just look at the real domain, that's still a mystery. But perhaps based on the way I phrase my sentences here, you have a solution to this problem. Why is this function, is this series expansion still not converging in the interval from -1 to +1, even though there's no discontinuity here in this graph? What's still happening? I see somebody nodding there in the back. That's true, so everything looks fine on the real axis, but if you look at this function in the complex domain, there are zeros, namely j and minus j. So even though everything looks fine in the real axis, if you look at this in the complex plane, you still have discontinuities. And it are these discontinuities that cause also the series expansion in the real axis to break down. Later on we will be talking a lot about series expansion in the complex domain. So these were just two things to give you some sort of flavor for why it would be very interesting to throw away the blinders, not just look at the real axis, but step into the wonderful world of the complex domain and complex analysis, where everything becomes much more obvious and much more clear. Okay, so that's the introduction, basically. Any questions on this? If not, let's start with the course proper, and let's now look at what it means to be a function of a complex variable. So let's look at functions of complex variable. So that's part 2. Part 1 was everything related to the Helmholtz equation. Now we have part 2, functions of complex variables. So we have a function f, not f of x, but f of z. Now by definition, z is a complex number. So we can write this as x plus jy, of course. But not only z is a complex number, also f of z is a complex number. It will consist of a real part and an imaginary part. So we can write this more explicitly as a real part u, which is then a function of the two variables x and y, and an imaginary part jv, which is again still a function of x and y. So this is the definition of a complex valued function. Nothing mysterious, very straightforward, and you see in essence a complex function is a shortcut for two real valued functions, u and v, of two real variables x and y. So it's just a shortcut. So for example, if you have a function u of x and y, which is x squared minus y squared, and v 2xy, so this would be one way to define a complex function, just by defining this u and v as a function of x and y. You can group them together more compactly as f of z being x squared minus y squared plus j times v being 2xy, and this is nothing more, nothing less than x plus jy squared, as you can see, simply by expanding the square, and this is z squared. So this is the same thing. Either you have the function f of z is z squared, which is very compact, or you specify a complex function by breaking it up into real and imaginary parts u and v as a function of two variables x and y. obviously our preference is for f of z equal to z squared. That's much more compact. You could also move the other way around, of course. If you start from a function definition involving f of z and z, for example, f of z is the product of z and the complex conjugate of z, you can ask yourself the question, what is the u and the v that correspond with this function definition? Well, that's also quite straightforward. You just expand this. The complex conjugate is x minus jy, and that gives you x squared plus y squared, which is the modulus squared of z, which is of course logical, and giving you u equal to x squared plus y squared, and v equal to 0, of course. So this is just definition of a complex function. Nothing mysterious, all very straightforward. Let's have a look. Let's go one step further. Now we have the functions, we have their definition. Let's play around with them. And one obvious thing we can do with these functions is take their derivatives. So how do derivatives in the complex plane work? Well, again, we can look for inspiration by stuff we know from the real plane. So for example, we can define the derivative f prime of z as this df over dz, which we could define as a limit of delta z going towards 0 of f of z plus delta z minus f of z divided by z plus delta z minus z, or just delta z if you want. So this is quite a sensible proposition. I hope you'll agree with me, because this is just a definition from derivatives in the real axis where we replace x by z. So that's the most logical thing we can do. Let's see how this works for these two functions that we've introduced earlier. So let's have a look at the first example where we had f of z equal to z squared. How would that work? Well, if we use our definitions, f prime of z, that would be the limit of delta z going towards 0 of f of z plus delta z. That would then be z plus delta z squared minus z squared divided by delta z. And that, of course, is the limit of delta z going towards 0, z squared plus 2z delta z squared minus z squared divided by delta z. And then we have these happy moments where we can get rid of some terms. And we can also divide everything by delta z. So it's just 2z plus delta z, not squared, just delta z. And that obviously is 2z, which is exactly the same as you would have with the derivative of the function x squared giving 2x, which is logical because basically the only thing we did here is replacing x by z. So that's very logical, very satisfying, but it leaves you wondering what's really so special about this complex analysis. If it's only replacing x by z, who cares? What's really special here? Well, it turns out that it's a bit more involved than that. If we look, for example, at our second example that we've had earlier, which was the function f of z, the product of z with the complex conjugate, or the modulus squared of the complex number. If we try to take the derivative of that function, let's see what happens. So we have the limit of delta z going towards 0, the modulus of z plus delta z squared minus the modulus of z squared, and everything should be divided by delta z. However, now we run into some problems or issues, because what's happening with the numerator? The numerator is always purely real, right? By definition of the modulus of the absolute value. Whereas this delta z, by virtue of it being a complex number, this is complex. And moreover, it depends on the choice of delta z. So you could pick a very specific delta z which was real, and then you would get a certain result. But you could also pick a very specific delta z which was not real or complex, and then you will get a complex number as a result. So depending on the choice of delta z, you either get a real number or a complex number. So depending on the choice of delta z, you would get a different final value for the derivative. So it seems that it's possible that the derivative of a complex function does not really exist, but depends very much on the choice of delta z, so on the direction of approach in the complex domain. So if we make a drawing of the complex plane xy, and we want to calculate the derivative of a function f of z at a certain point z, we can approach this point z in many different ways. We can either approach it like this, for example, and that's a case where x does not vary, where delta x is equal to 0. Or we could approach this function like this, where delta y is equal to 0. And as we've seen from the example of modulus squared, it's not a priori guaranteed that these two directions of approach give the same value for derivative. We have something a little bit similar in real analysis, but there it's of course not so involved. If you have a function and you want to calculate the derivative, you can either approach this point from the left or from the right, and most of the time that gives you the same result. But there are some very pathological cases where you have a discontinuity, for example. If you want to calculate the derivative here in this point, it's also not defined. You have a different value whether you approach from the left or the right. But here, in this 2D case involving the complex plane, it's a lot more complex, obviously, sorry for the bad pun, because you can approach not only from left and right, but also north, south, east, west. So the direction of approach can be any direction in the complex plane. So it would be good to figure out some sort of criterion that would allow us to determine whether a function has a uniquely defined derivative, independent of direction of approach. And then we can say it's a well-behaved function which has a derivative. So let's do this in 2 steps. Let's first derive a necessary condition for this. So if we have a function where the derivative is well defined and is independent of direction of approach, then a fortiori this should be true for 2 special directions that we choose, namely these 2 directions which I've drawn here, delta x equal to 0, delta y equal to 0. So if it's true you get the same result for all possible directions, you will certainly get the same results for 2 very specially chosen directions, namely the horizontal one and the vertical one. So if this is true, let's just see what happens by demanding that they give you the same results. So let's first look at the direction of approach delta y equal to 0, which is this horizontal approach here. Then what we have for our derivative is the limit of delta z going towards 0 of delta f over delta z, which is the limit of delta z going towards 0. If we break this up in real and imaginary components, we have delta u plus j delta v divided by delta xx plus j delta y. So this is the most general form of our derivative. But now we're looking at a very special case where we approach this point horizontally, so delta y is equal to 0. So we can get rid of this here. So if delta y is equal to 0, then delta z is just delta x, so we get the limit of delta x going towards 0 of delta u divided by delta x plus j delta v divided by delta x. So in the very special case of a horizontal approach, this is what our derivative reduces to. And this you should immediately recognize, right? These are the partial derivatives of u with respect to x plus j times the partial derivative of v with respect to x. So this is the result in general that you would get from approaching this function horizontally with delta y equal to 0. Now we can also calculate what happens if delta x is equal to 0. We'll get a different result. And then for the derivative to exist, we just impose that these two different results are the same actually. And then we'll get a certain condition that needs to be fulfilled if we have a function where the derivatives exist and are independent of direction of approach. So let's look at our second direction of approach. We again have, of course, the limit of delta z going towards 0 df over dz, limits delta z 0 delta u j delta v divided by delta x plus j delta y. But in this case, we throw out delta x because delta x is equal to 0. And then we get the situation where we now consider the limits of delta y going towards 0 of, what do we have left? Well, we divide by j, here we have, so minus j du dy plus dv dy. So this is a case where I have to be really careful with my handwriting and distinguishing u's from v's. So I'm doing my very best here. And if we now simplify this, we end up with partial derivatives. This time the partial derivative of v with respect to y, just flipping the order here, minus j, the partial derivative of u with respect to y. So these are the two results you get for these very well chosen directions of approach. Now, if we have a function where the derivative exists and is unique, then these two numbers, these two should be the same, right? So we have a complex number on both sides. We should ask that the real part is equal to the real part and the imaginary part is equal to the imaginary part. So if we impose these conditions, we get that the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y. And we should also get that the partial derivative of v with respect to x is equal to minus the partial derivative of u with respect to y. So if we have a function where the derivative is well defined and independent of direction of approach, these conditions should hold. These conditions involving partial derivatives. These conditions, they have a name. They're called the Cauchy-Riemann conditions because of the two mathematicians who worked on it, Cauchy and Riemann. And functions which satisfy these conditions, they're called analytical functions, or they're sometimes also called holomorphic functions. If you look at Dutch textbooks, you will typically more see the term holomorphic functions. Anglo-Saxon textbooks more speak about analytical functions, but they're functions which satisfy the Cauchy-Riemann conditions and which have a very well-defined derivative. They're more like the natural extension of this concept of C-infinite functions, which we've seen before the break in real analysis. So far we have the fact that these conditions are necessary. So if the derivative exists, then the Cauchy-Riemann conditions hold. Now we still need to do it the other way around. If the Cauchy-Riemann conditions hold, does that automatically mean that the derivative is independent of direction of approach? So that's still the second piece of the puzzle we need to take a look at. So let's have a look at the fact whether or not this condition is sufficient. So at first we will be playing around a bit with just manipulating symbols, total derivatives. So the total differential here of f, of course, since f depends on x, we can write this as follows. And since f also depends on y, we can write this as follows. This is purely symbolic manipulation, if you want. F consists of two parts, u and v. So we have du dx plus j dv dx. dx. So these are partial derivatives here. These are differentials. So just juggling here. So we have du dy plus j dv dy. And this takes care of everything what's happening with y. So this is df. What we're interested in is df over dz. So we just copy and paste this and divide by dz. So du dx plus j dv dx dx plus partial derivative u di j dv dy, and we divide everything by dz, which is of course dx plus j dy. Next step, we will divide for fun just everything by dx, and what we then get, we have du dx plus j dv dx. I should do copy and paste, but okay. J dv dy, and then we have here dy over dx, and then we divide everything also in the numerator. We have dy over the dx. So far the only thing we've done is just some symbolic manipulation of these quantities, juggling around with some terms and factors. But what we're essentially after is that we're needing to prove that if the Cauchy-Riemann conditions are fulfilled, that then the derivative here is independent on the direction of approach. So this is what we need to prove in words. The question is, where is this direction of approach encoded in the formula we have here? So how do we translate this concept of direction of approach into mathematics? So have a look at this formula and let me know where you think the direction of approach is encoded. So we have lots of partial derivatives, plus signs, j, dy over dx. So which would be a good candidate to encode direction of approach? Where is that encoded? Remember, previously, for the necessary conditions, we had a look at two different directions of approach, one where delta x was 0 and one where delta y was 0. So what encodes direction of approach? No one? Sorry? So, in fact, so if we just look back to what we had here, so here direction of approach was something which had to do with delta y's and delta x. So we had a very special direction of approach where either delta y was equal to 0 or delta x was equal to 0. We could also have directions of approach where delta y was equal to delta x. So directions of approach are encoded in these delta x's and delta y's, or put it in a different way, they are encoded in the ratio between the delta x's and the delta y's. Now in our terminology here, we're not talking about deltas but the differentials. So this here is where the direction of approach is encoded. Either this factor is 0 or infinity or 1 or whatever, but depending on the direction of approach you choose, you have a different ratio between delta y and delta x, and this is where the direction of approach is encoded. So we need some way to prove that if the Cauchy-Riemann conditions hold, that this term disappears from our equations. That's our aim, right? Everything clear so far? So this is the aim. Let's see if this indeed works. So what happens if the Cauchy-Riemann conditions hold? can we then simplify that expression? Well, if we apply our Cauchy-Riemann conditions, for example, to this thing here, so we have du dy plus j dv dy. If you go back to the Cauchy-Riemann conditions, we start out by du dy. So du dy, this would be minus dv dx. Minus dv dx. And then we have j dv dy. If we look back here, dv dy is equal to du dx. And then we can just bring j out of our brackets here to have du dx plus j dv dx. This is equivalent. Now that we have this, we can simplify what we have upstairs there. So we have df dz. We have 2 times this factor here, du dx plus j dv dx. This also now appears here. That's good news. We can factor this out. So we can factor out du dx plus j dv dx. We have that once with the prefactor 1 and once here with our prefactor j dy dx. This is for the numerator. What about the denominator? The denominator is 1 plus j dy dx. And that's excellent news because we can cancel these factors here. So df dz turns out to be just du dx plus j dv dx. So if the Cauchy-Riemann conditions hold, we've proven that the derivative, the f dz, is independent of the direction of approach, independent of dy dx. And moreover, we have an extra way of calculating the derivative. It turns out you can just construct it by calculating the partial derivatives with respect to x. So dv dx plus du dx plus j dv dx. So these are the Cauchy-Riemann conditions. Very important. If a function satisfies these conditions, it means that the derivative exists and is independent of direction of approach. And we have these so-called holomorphic or analytical functions, which is a very special class of functions that we will be talking about a lot in the future. Okay, I've been talking a lot so far. I think it's high time that you guys did some exercises. So what I will be doing is I will be writing 3 different functions down, and my question to you is, are the Cauchy-Riemann conditions for these functions satisfied? And if so, calculate their derivatives. And later on I will be calling for some volunteers to write down their solutions on the blackboard, or this more modern version that we have of it. So our first function is our friend f of z is z squared. We encountered this function before. Our second function is f of z is z times the complex conjugate. We also encountered this function before. And the third one is f of z is the real part of z, so just x. So these 3 functions, see if the Cauchy-Riemann conditions are satisfied, and if they are, calculate their derivatives. So this is over to you now. You can either do the blackboards or record it for posterity. Do you prefer the blackboards? Yeah. That's too bad for the people following at home or YouTube later on. face with the eraser at the top.
Okay. This is good.
Okay. Okay, so the Cauchy-Riemann condition is solved. That's good news. Meaning that the function has a derivative.
Yes.
Can you calculate the derivative?
And how to move it?
Just page down on the arrow keys. I find easier. Yeah, okay, we did that earlier, of course. But we can also do that. Thank you. What you could also use is the formula f prime of z, partial derivative du dx plus j dv dx. This is also a formula that we showed earlier. And this is then 2x plus j 2y, and this is also 2z. So that's the same. So it's all very consistent, which is good news. Second volunteer for f of z is z times z prime. Debating whether or not to volunteer. I think we have a volunteer. And you can do the third then. So you immediately see that the Cauchy-Riemann conditions don't hold. So it also stops here, so don't be tempted to calculate f prime of z by the formula in u dx plus j dv dx, because that does not hold. The derivative is not independent of direction approach. So the function modulus z squared is not a holomorphic function. And then your colleague can do the third one. Okay. So also here the Cauchy-Riemann conditions don't hold. So from our examples, the ones down here, we had one that was holomorphic, f of z is z squared, and the other two ones were not holomorphic. So I'm going to let you in on a little secret now, a little intuition that you can build in order to help you determine when functions are holomorphic and when not. If you have a function which is like f of z is z squared, formed by taking a real valued function and just replacing the x by the z, then there's a very good chance that this will be a holomorphic function. If, on the other hand, you have functions which try to look into the complex number and break it apart, like for example the real part of z or the complex conjugate of z, if you have stuff like this, as soon as explicitly the real part or the imaginary part appears, or as soon as the complex conjugate appears, then you have functions which are typically not analytical. So these are some things that can help you figuring out whether functions are analytical or not without having to go through the trouble of calculating the Cauchy-Riemann conditions. And it goes without saying that a function which is holomorphic also needs to be nice, in the sense that it needs to be continuous, no singularities, because otherwise if you have a singularity, the direction of approach also plays a role in calculating the derivative. Just like we had, for example, in this case of real valued analysis. So the function needs to be continuous, nice and well behaved. Any more questions about this? The exercise for the analytical functions and the fact that the Laplacian of the part should be 0 that I leave for at home. If there are no questions, also not at the back there, no questions? No questions. Then we can move on to the final part of what I want to discuss today. So we had the definitions of functions, we had the definitions of derivatives. The next step you want to take, of course, as a true mathematician, is taking the integrals of complex functions. So how does that work? Integrals of complex functions. Well, we have, of course, our real valued things to take inspiration from. So rather than writing the f dx, we can write, rather than writing f of z dz, we can write, rather than writing f of x dx, we can write f of z dz and have an integral. Now this time it's a bit more complicated in the sense that the integral is not, for example, from a to b, but rather takes a certain path. So if you have the complex plane, x and y, you go, of course, from an initial point to an end point, but you could take different paths to get there. So the path, the contour C, is very important in complex analysis. Now, by definition, what's the definition of this complex integral? It's a line integral because it follows a line segment path. We just split it into its components. So we just say that f of z, in fact, is a stand-in for u of x and y plus j v of x and y, and dz of course is a stand-in for dx plus j dy. That means we can split this into two real valued line integrals, one involving the real parts and one involving the imaginary parts. So we have u of xy dx minus v xy dy. That's a first part. And then we have plus j, a second part for the imaginary stuff, which is v of x and y dx plus u of x and y dy. So these are the two integrals. They're both real valued integrals. You know how to calculate them, line integrals, right? We've discussed this a little bit also before the break. And don't be confused here. Here appears dx and dy. They're not independent variables, but they depend very much on the integration path, obviously. Remember the story from direction of approach and stuff like that? So you might also recall from your earlier career that the way you solve these line integrals is by parametrization. So if you have your contour C, you typically have then a real parameter, for example s, running from s0 at the start to s1 at the end, and you just parameterize these curves so that in the end there's only a single ds which then runs along the curve rather than a dy and a dz, which are independent. So this you should have seen in your earlier career. But just as a quick review, let's solve an example. Let's solve the example of an integral of z to the power of n dz, and the contour we're going to be studying is in fact a circle with a radius little r and a contour which is in the counterclockwise direction, centered around the origin. So we identify the contour here. Something which is very typical for complex analysis is that if you have a closed path, a closed integration path, they indicate this by having an extra circle here in this integral symbol. So this is for a closed contour integral. Okay, how are we going to solve this? Remember parameterization. So we have a variable z which is happily running around here, around that circle. So we can parameterize it by the angle theta. So we can say that z is r exponential j theta, where r is of course a constant, and theta is our parameter, which parameterizes this curve and runs from 0 to 2 pi, for example. So based on this parameterization, we can go to a regular boring integral, if you want. So an integral of theta running from 0 to 2 pi of z to the power of n, of z to the power of n dz. Now z being parameterized by r exponential j theta, that means that dz, of course, if theta is the variable, that means that dz is r j exponential j theta, and z to the power of n is of course r to the power of n exponential j n theta. So this is how we replace our complex argument z by something where only a real parameter theta changes. So if we now combine this, we have j, we have r to the power of n plus 1, which is a constant, so we can bring that nicely out of our integral. We still have an integral from 0 to 2 pi exponential j n plus 1 times theta d theta. Okay, let's solve this integral. There are of course two different situations that we have to take into account. First one is where n is different from -1. Then we can simply solve this. We can divide by n plus 1 in this case. So we have jr n plus 1 divided by j n plus 1, and we need to evaluate the integral here, exponential j n plus 1 theta. We need to evaluate this between the boundaries 2 pi and 0, which is equal to, who votes for 0? Who does not vote? All the rest. It's indeed the guys that raise their hands. It's indeed 0, simply because this exponential j theta is a periodic function with periods 2 pi, right? So this is 0. The exponential, complex exponential is periodic with 2 pi. So that's not a lot, 0. But what would happen if we look at the very special case where n is equal to -1? Then we cannot, of course, divide by 0, otherwise we would incur the wrath of all the mathematics gods. So we need to take a bit more care to evaluate this. So this is the integral of dz over z. But if you then look at this integral, we have j, of course. We have r to the power of 0, which is 1, so that doesn't figure in formulas. We have our integral from 0 to 2 pi. And again, we have exponential to the power of 0, which is 1. So we just are left with d theta. And that's an integral you know how to calculate since kindergarten, right? So this is just 2 pi j. This is a very simple integral. So this integral of z to the power of n is 0, except when n is equal to -1, and then it's 2 pi j. Some remarks. First of all, these results are independent of the radius r, so whether you have a tiny circle or a huge circle, the end result is the same. And also something very important, as this might look like a very trivial exercise, it turns out that the results from these exercises are extremely important and will later on lead to lots of interesting theorems. So for example, it's very special that you only have a result for n equal to -1, a non-zero result. These things will come back later on, so remember these. They will be important later. Okay, to wrap up this class, let's look at a first important theorem, which is called Cauchy's theorem. So, Cauchy's theorem. Cauchy is very prolific when it comes to complex analysis. You might remember the Cauchy-Riemann conditions, I hope. There's not only Cauchy's theorem, as we will discuss now. There's also, for next week, Cauchy's formula. So he was very productive in the complex plane. But personally, I can never remember which is the theorem and which is the formula of Cauchy. So I will be taking a rather non-standard approach here when it comes to nomenclature. And I will be calling Cauchy's theorem Cauchy 1, because it's the first one we encounter, the simple one. And then the next one, Cauchy's formula, I will be calling Cauchy 2. This is something you will not find in any other book. This is just me being lazy. Okay, there you have it. I think it's better to fill your brain with important stuff rather than distinctions between theorems and formulas and whatever. Okay, what does Cauchy number 1 teaches us? Well, it deals with C, a closed contour, as many of these theorems do. And we have a function f of z, which is analytical inside that contour. So we have our potato-shaped contour. Doesn't matter what the shape is, as long as it's closed. And we have a function f of z, which is nicely well behaved in the inside of the contour. It's a holomorphic function there. And Cauchy number 1 tells you that the contour integral of f of z dz in such a case is 0. So remember, this goes back a bit to what we had earlier. If you have positive exponents here, z squared, c to the power of third, we already saw indeed that this gives you 0. So Cauchy's theorem is like a generalization of this, if you want. So let's try and prove this. Okay. First of all, we have, of course, our definition of f of z dz. Just as we had earlier, I will split this up into real and imaginary parts. So we have u plus jv dx plus j dy. So this is what we did earlier. So it's the integral of u dx minus v dy. Let's make it a bit more distinct. That's the first part. And then we have a second part, which is the imaginary part, which is u dy plus v dx. Okay, so this is what we did earlier. So what we have to work with, we start from this definition of f of z, and somehow we also need to make use of the fact that the Cauchy-Riemann conditions hold. The Cauchy-Riemann conditions, they are all about partial derivatives, as I hope you remember by now, and I do not see any partial derivatives in this definition of integral at this stage. So our first task is to massage this function, this formula, in such a way that we get partial derivatives here, so that we can make use of the Cauchy-Riemann conditions. So that's the first step. How are we going to achieve this? Well, we go back to our old friend Stokes, which we had before the break, which tells us that the integral over a surface of the curl, of the rotor of a vector field, dz, that's equal to an integral of the vector field itself at C being the boundary S. So this is indeed something which relates a regular function so which relates a function without any derivatives here to something which does involve derivatives. So let's see if we can make use of this. Since we are working in the complex plane, it also means that we're going to restrict this to a purely two-dimensional case. So our surface S is contained in a plane. It's not like a pancake which is contained in the three-dimensional plane. So rather we will be writing this just in the 2D plane with A consisting only of an X component, a X and a Y, and 0 for the Z components, and for the S, that should be the S of course, and for the S, which will then be perpendicular to the plane, so perpendicular to X and Y, that would be a vector along the Z, so 1Z, and the size of the patch is the product of the X and the Y. So this is what we get from living in a two-dimensional world. So if we then simplify this, we have the integral, the surface integral of the curl of A. ds is just 1z dx dy. And for the right hand side, we have our contour integral, if we use this terminology with the circle in the integral sign again. So we have ax ay 0 times the dl, but the dl, that will just be dx dy dz, right? Okay, simplifying this a bit, starting with the right hand side here, we have our contour integral of ax dx plus ay dy. That's the right hand side that now becomes the left hand side. And then for our surface integral S, we only need to look at the z component of the curl. And if you look back at the formulas that we started this class with, the z component of the curl, that gives you d ay dx minus d ax dy dx dy. Now these formulas, they are indeed what we're after, because they give a relationship between what we start out from here, which is just a line integral which does not involve any partial derivatives, and we can convert this into a surface integral which does involve partial derivatives, where hopefully we can then let the guys Cauchy and Riemann loose on, and then they will prove that the integral is indeed 0. So this is what we're going to do. We'll do this in 2 steps. We'll first tackle this part here. And actually, I won't tackle the second part. I will leave that for an exercise for you at home. So we're looking at u dx minus v dy. If we identify that form with the form we have here, and for the first part, this means that this ax now should take the form of u, and ay should take the form of minus v in order to be able to apply this to the first term. So we're interested in u dx minus v dy, right? If we replace that with our a's, we get that this is equal to ax dx plus ay dy, right? Our little extra result that we derived from Stokes tells us that this is equal now to a surface integral. I just copy and paste from what I have up here. dy dx minus dax dy. dx dy. If I now go back to my u's and my v's, I get d, okay, ay is minus v, so minus dv dx. My ax is u, so I get minus u dy. dx dy. And if you go back to our friends, the Cauchy-Riemann conditions, you will see that this is indeed 0 coming from Cauchy-Riemann, or at least one of the Cauchy-Riemann conditions. And then similarly, you can make a different choice for ax and ay to tackle the second term in that equation, and also proving that the second one is equal to 0. So this is the proof of Cauchy 1. If you have a function which is analytical and you have a closed contour, the contour integral is equal to 0. Any questions on this? There's not really time to tackle the second part of Cauchy, so we'll do that next week. So next week I hope to see you all again physically present as opposed to just digitally. Oh, question, yeah, good. I'm sorry? I can certainly scroll down. Yeah, there you have it, so I'll leave it for you to copy. Okay, thank you very much, and see you next week.